Hello dear student, this is Kanchan Vishramji Kumbhalkar, Assistant Professor of Sri Shivaji College of Arts, Commerce and Science, Akola. I belongs to the Department of Chemistry and I am here to taught you about the BSc first year, first sem, Unit 6, that is gaseous state and phase rule. This is the syllabus of A part, that is gaseous state, and this is a B part, that is phase rule. So let's start with the unit number 6, lecture number 2, that is gaseous state and phase rule. Today's topic are some definitions. First definition is root mean square, that is RMS velocity. Suppose there is a container and in container there is a gas has been filled. There are n number of molecules are there. So each molecule can move in all possible direction with a various velocities. So it is impossible to calculate the exact velocities, or average value velocity cannot be easily calculated. Therefore, to help that condition, we have to mention the root mean square velocity. So, in general, in a gas, there is a large number of molecules. They are in a continuous state of rapid motion in all directions and which is having a widely varying velocities. It is impossible to work with this condition. Hence, it is required to take an average value of the velocity. The ordinary arithmetic average velocity is not taken, but the molecules are supposed to possess velocity which is such that it is a square root of mean of squares of different velocities possessed by the molecule, and this velocity is known as the root mean square velocity, that is RMS. For example, capital C1, C2, C3 etc. are the velocities of n number of molecules up to the Cn. Then the root mean square velocity, that is U, can be written as it's a root, that is square root of mean of squares of velocity. So this is the root, it's a square root. These are the velocities, various velocities of the n number of molecules. This is the average or mean, and C1 square, C2 square, C3 square, this is the square. There is the root mean square velocity. So U is nothing but a root mean square velocity. Now, deduction of molecular velocity from kinetic theory. Now, in previous lecture, in equation 1.9, which describe for n number of molecules, it has been given that the PV is equal to 1 upon 3 mn U square, where P is the pressure, V is volume, m is the mass of molecule, n is the number of molecules, U is the RMS velocity. So, for n number of moles, the PV can be written as 1 by 3 mn U square on the basis of equation 1.9. Since the overall mass molecular weight of the compound can be considered as the capital M is equal to N into M, where N is the number of moles and M is the mass of each and every molecule. So, the total mass can be a product of N and M. Now, put the value of Nm as a capital M in this equation. So, this equation becomes PV is equal to 1 upon 3 capital M U square. So, by means of this, you want a U value. So, take all the terms except U to the another side. So from this equation, the u value can be written as in the form of PV and m is equal to u equals to under root of 3 PV upon m, where u is root mean square velocity, that is RMS velocity, P is a pressure, V is a volume of gas, and m is the total molecular mass of a gas of a particular container which containing a n number of moles of gas. So this is the equation for that of the root mean square velocity. If d is equal to m by v, where d is the density of a gas, density is equal to mass upon volume. So density mass upon volume, so this equation 1.1 can be written as u is equal to 3p upon d. So this equation can be modified in the sense of d also. Now the next point is the Maxwell-Boltzmann law of distribution of molecular velocities. In a gas, the molecules move with the different velocities because due to collision with one another, the velocities of molecule go on changing continuously. Due to collision, the velocity of molecule may vary from 0 to very high velocities. On the basis of probability consideration, Maxwell and Boltzmann in 1850 gave an equation showing the distribution of the velocities among the molecule. So there is a Maxwell and Boltzmann in 1815 give an equation which show that dnc upon n dash is equal to 4 pi in bracket capital M upon 2 pi RT e to the power minus mc square upon r2 RT c square dc. Now dnc upon n dash is nothing but the fraction of total number of molecules n dash having the velocity between the c and c plus dc, and capital M is the total molecular weight of gas, capital T is the absolute temperature of gas system, and capital R is the gas constant. Now this 1.15 equation, divide that 1.15 equation by means of the DC. So we get 1 upon DC into dnc upon n dash, which is equal to 4 pi capital M upon 2 pi RT e to the power minus mc square 2 RT c square dc get cancelled. So this is the another equation. This has been putting as a 1.16. The left hand side of equation 1.16 represent the probability P, and it is described the probability of finding the molecules with the velocity c. So hence the distribution of molecular velocity can be represented graphically, which has been shown in this figure 6.3. So probability, that is capital P, having the various velocity is plotted as a function of velocity c at a definite temperature. So in this graph there are the three terms has been mentioned here. The P versus C graph is there, where P is the probability, C is the velocities, and there are the three various temperature has been mentioned here, that is T3, T2 and T1. As compared to the T1, temperature T2 is higher and T3 is the most higher temperature as compared to the T1 and T2. So when we are considering according to the Maxwell and Boltzmann law of distribution of molecular velocity, such type of graph has been observed here. So when we are considering the T3 temperature, the most probable velocity can be considered this one. So with respect to the temperature, the most probable velocity or the probability having a particular velocity can be differ. In figure 6.3, which indicate that the probability P increases with increasing the velocity. So when we are increasing the velocities, the probability is also increases, but up to a particular limit. Means with respect to increase in velocity, probability continuously increases, but at a particular point. and after that the probability has been continuously decreases. So in this diagram, in this graph, the probability P increases with increase of C and passes through a maximum and then begin to decrease. There is a increases and at the elevated point then there is a decreasing. In all the cases, it can be understood from the curve that very few molecules possess either very low or very high molecules. So probability of molecules having a very high velocity or very low velocity is considered as a less. So probability, so it has been given that very few molecules possess either very low or very high velocities, and the majority of the molecules have velocities corresponding to the peak of the curve. The velocities corresponding to the largest probability of the distribution curve is known as the most probable velocity. So this is the maximum probability. This is the lowest velocity and this is the highest velocity regarding with this curve. So the point where the maximum probability is there, or the velocity at which the maximum number of molecules possess that velocity, that is known as the most probable velocity. So in this figure the most probable velocity is also shown, means the velocity corresponding to the largest probability of the distribution curve is known as the most probable velocity. This figure also shows that the most probable velocity in a gas varies with the temperature and it is increases with rise in temperature. So when there is an increase in temperature, then the most probable velocity has been increases. So the velocity value is directly proportional to the increase in temperature. So as there is an increase in temperature, the most probable velocity is also increases. The number of molecules possessing the most probable velocity decreases with the increase in number. When we are talking about the temperature effect, as there is an increase in temperature, the most probable velocity increases. Means when we are talking about, this is T1 curve, this is T2 curve and this is T3 curve. T3 is the highest temperature as compared to T2 as compared to T1. This is the range of temperature. So when we are talking about the T1 temperature, this is the range of most probable velocity. But the velocity of most probable molecules is considered as a low as compared to for that of the T2 and as compared to for that of the T3. Means at a higher temperature, the most probable velocity value, velocity of the most maximum molecules are high as compared to T2 as compared to T1. But the probability of molecules to be found at that most probable velocity is higher for a T1. Means here is the probability is high. More number of molecules show this type of velocity. This velocity has been shown by less molecules because the probability has been decreases. Here is the probability value decreases. So there is a probability number of molecules of having a most probable velocity has been decreases with the increase in temperature. So this is the study of this 6.3 graph, that is Maxwell Boltzmann law of velocity of distribution of molecular velocity. Now the most probable velocity, mean velocity and root mean square velocities. The first point, it can be shown by mathematical calculations that the most probable velocity c is given by expression c is equal to under root 2 RT upon m. R is gas constant, T is absolute temperature, capital M is the total molecular mass, and C is nothing but a most probable velocity. Most probable velocity means the velocity possessed by the maximum number of molecules, that is known as the most probable velocity. Next one, the mean or average velocity. Suppose there are n numbers of molecules and which containing a various velocities, for example C1, C2, C3 etc. up to the Cn. So the average of all these velocities can be considered as the mean or average velocity, and which is indicated by small v, that is v is equal to C1 plus C2 plus C3 up to the Cn upon the total number, that is n number of molecules. So v is equal to, v is nothing but the mean or average velocity of molecule of a gas, and it is formulated in such a way. And the last definition is the root mean square velocity, that is u. As earlier stated, it's a root mean square of the velocities. Suppose there are C1, C2, C3 up to the Cn number of individual velocities of molecule of a gas, n number of molecules. So its square root of average of squares of this velocity is nothing but a root mean square velocity, which is indicated by u. Now there is an equation. From that equation it has been shown that the root mean square velocity u is equal to 3 upon RT upon m, mean velocity v is equal to 8 RT upon pi m, and most probable velocity is given as 2 RT upon m. So you must remember all these terms, all these equations regarding the root mean square velocity, mean velocity and most probable velocity. Referring to above three relations, by considering all these three equations or relation, and by putting the values of r and pi in these all three equations, the most probable velocity, mean velocity and root mean square velocity having the relation that it is proportion to 1 is to 1.128 is to 1.224. So this is the relation between the most probable velocity, mean velocity and root mean square velocity. Thus root mean square velocity is the greatest of the three, followed by the mean velocity and most probable velocity. From this thing it has been observed that the value of the greatest root mean square velocity is greatest one, then mean velocity, and the last one most probable velocity. So this is all about for this lecture number 2. We will meet at the third lecture. So till then, take care. Thank you very much.